Imagine opening the deepest photograph ever taken of space and finding something that should have been almost impossible. Not a planet, not a star, not a strange signal from aliens. A galaxy, a real galaxy, shining from a time when the universe was still supposed to be young, dark, simple, and unfinished. Its light began traveling when cosmic history had barely started. Earth did not exist. The sun did not exist. The Milky Way had not become the galaxy we know. And yet, in that ancient darkness, something had already gathered gas, built stars, produced heavy elements, and grown bright enough for the James Webb Space Telescope to see it across more than 13 billion years. That is why this discovery feels so unsettling. Because if a galaxy could become this, developed this early, then something in our picture of the beginning may be missing. Maybe the Big Bang story is not as simple as we thought. Maybe the first galaxies grew faster than our models allowed. Or maybe Webb is showing us the first crack in a timeline we believed was almost settled. Before we begin, if you enjoy calm journeys through space, time, and the mysteries hidden in the early universe, subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. Somewhere, someone may be hearing this under a night sky, while someone else is listening in the middle of the morning. Tonight, you are watching the Just About Space channel, talking about the James Webb discovery that could change the universe. To understand why one small red object in a deep field image became such a serious problem, we have to begin with a quiet fact about astronomy. A telescope does not only look across distance, it looks backward through time. When you look at the moon, you see it as it was a little more than 1 second ago. The sunlight bouncing off its surface needed that long to reach your eyes. When you look at Jupiter, you are often seeing it tens of minutes in the past. A star 1,000 light years away is not being seen as it is right now, but as it was when its light began the long crossing toward Earth. The same idea becomes almost impossible to imagine when we talk about galaxies near the edge of the observable universe. Some of the faintest smudges in Webb's deepest images are not merely far away. Their light has been traveling for almost the entire age of the cosmos. By the time that light reaches us, it has crossed expanding space, stretched in wavelength, dimmed by distance, and carried with it a message from an era that no human mind can truly picture. That message is not written in words. It is written in color. It is written in missing light. It is written in spectral lines, sharp breaks, and faint infrared signals pulled out of darkness by instruments colder and more sensitive than anything humans had placed in space before. For most of human history, the early universe was not a place we could inspect directly. We could imagine it, calculate it, and reconstruct it from evidence. But the first galaxies remained hidden behind the limits of our telescopes. Hubble changed that picture by revealing deep fields filled with remote galaxies. But even Hubble could not see everything. At some point, the most ancient light was stretched beyond the visible range. This is where James Webb entered the story. Webb was not built simply to take sharper pictures of beautiful nebulae, although it does that extraordinarily well. Its deeper purpose was to look into the infrared universe. Light from the first stars and galaxies began as ultraviolet, or visible light, but the expansion of space stretched it into longer and longer wavelengths during its journey. By the time it reaches us, the oldest starlight has become infrared. A normal visible light telescope is almost blind to that first glow. Webb was built to see it. Its golden mirror gathers a whisper of ancient radiation. Its instruments split that whisper into colors. Its position far from Earth keeps it away from heat and interference. Its sunshield helps keep the telescope cold enough to detect faint infrared signals that would otherwise vanish into noise. And with that power, Webb began looking into a part of cosmic history called cosmic dawn. The name sounds gentle, almost poetic, but the reality was violent, strange, and uncertain. Cosmic dawn was the period when the first stars and galaxies began to shine after the long dark ages. Before that, the universe was not empty, but it was dark in the ordinary sense. There were no stars like the sun, no spiral galaxies, no planets, no glowing nebulae, only expanding space, invisible dark matter, hydrogen, helium, traces of lithium, and the slow pull of gravity trying to turn tiny differences into structure. The early universe was not perfectly smooth. Small density variations existed, tiny uneven places where a little more matter collected than elsewhere. Gravity amplified those differences. Dark matter gathered first, forming invisible scaffolding. Gas fell into those dark matter halos. In the densest regions, the gas cooled, collapsed, and eventually became hot enough for nuclear fusion. That was how the first stars were born. But these first stars were not likely to be calm, sun-like stars. Many models suggest they may have been enormous, short-lived, and extremely bright. They formed from gas that was almost pristine, because the heavier elements had not yet been made in large amounts. Elements such as oxygen, carbon, silicon, and iron are not ordinary starting ingredients for the universe. They are forged inside stars and scattered by stellar death. That fact matters deeply. When astronomers detect heavy elements in a very early galaxy, they are not merely finding chemistry. They are finding a history. They are seeing evidence that stars had already formed, lived, exploded, or shed material, and enriched the surrounding gas before the light we now observe ever left that galaxy. Oxygen, in this context, is a cosmic timestamp. Dust is another clue. Dust sounds ordinary because it covers shelves and floors on Earth. But cosmic dust is made of tiny solid grains containing heavier elements. It does not appear in large quantities in a universe made almost entirely of hydrogen and helium. Stars have to manufacture the raw material. Supernovae, stellar winds, and dying stars have to spread it. Galaxies need enough time to cycle matter through birth, fusion, death, and recycling. So when Webb sees a galaxy too early, too bright, too large, or too chemically developed, the question becomes sharper. How did it get there so fast? That question has followed James Webb since its first deep images of the early universe. At first, the excitement came with confusion. Webb seemed to be finding more bright early galaxies than many astronomers expected. Some looked surprisingly massive. A few appeared so mature that headlines began to claim the Big Bang had been disproven, broken, or thrown into crisis. Those headlines spread quickly because the idea is irresistible. A telescope looks farther back than ever before and finds galaxies where they should not be. The foundation shakes. The beginning changes. The biggest theory in cosmology collapses under a red dot in a deep image. But science is usually stranger and slower than that. The Big Bang is not just one claim that galaxies formed at a specific speed. It is a broad framework supported by many lines of evidence. The expansion of space, the cosmic microwave background, the abundance of light elements, the large-scale distribution of matter, and the way the universe cooled from a hotter, denser state. A surprising early galaxy does not instantly erase all of that. Yet, it can still be deeply important, because sometimes a discovery does not break the whole house. It shows that one room was built differently than we thought. It tells us that a process we believed we understood was faster, messier, more efficient, or more extreme in the beginning. That may be what James Webb is doing. It is not simply showing us the early universe. It is forcing us to ask whether our timeline of the first galaxies was too slow. The object that made this question feel especially urgent is known as JADES, GS Z140. The name is not beautiful. It sounds like a label on a storage box. not one of the most distant known galaxies ever seen. But inside that technical name is a remarkable story. JADES stands for the JWST Advanced Deep Extragalactic Survey. It is a major observing program using Webb to study distant galaxies in the early universe. The survey points Webb at carefully chosen regions of sky, not because those patches look dramatic to the naked eye, but because they allow astronomers to peer through relatively clean windows into deep cosmic time. In one of those fields, astronomers noticed a source that looked strange. It was extremely faint by human standards. You could not look at the sky and see it. In the image, it was just a tiny feature among thousands of galaxies and points of light. Yet its colors suggested it might be incredibly far away. Far away in this case means ancient. The candidate appeared to have a very high redshift. Redshift is one of the most important words in cosmology because it tells us how much light has been stretched during its journey through expanding space. A low redshift can mean a relatively nearby galaxy. A very high redshift means light from a time when the universe was much younger. But candidates are not enough. Early galaxy hunting is full of traps. A red object might be a truly distant galaxy, or it might be a dusty, less distant object pretending to be ancient. Light can be blended. Noise can confuse the measurement. A source can look more dramatic in an image than it really is. This is why astronomers need spectra. A spectrum is not just a picture, it is a fingerprint. Instead of asking what an object looks like, spectroscopy asks how bright it is at different wavelengths. Certain features in that light reveal redshift, chemistry, ionized gas, and sometimes the physical processes powering the glow. With a good enough spectrum, the universe cannot lie as easily. Webb's NIR spec instrument observed JADES, GS, Z140 for almost 10 hours. That may sound long, but for something this ancient and faint, every hour mattered. The telescope collected the galaxy's light until a clearer pattern emerged. The result was extraordinary. The galaxy's redshift was measured at about 14.32. That corresponds to a time less than 300 million years after the Big Bang. Less than 300 million years. For a human life, that number is impossibly large. For the universe, it is infancy. The universe today is about 13.8 billion years old. Seeing a galaxy at less than 300 million years after the Big Bang is like seeing a person in the first days of life and finding signs of achievements that should have required years. The comparison is imperfect, but the emotional effect is similar. The timeline feels compressed. JADES, GSZ140 was not only distant, it was luminous. That is what made it so powerful as a discovery. If it had been only a tiny, dim, primitive object, it would still have been important. It would have confirmed that galaxies existed very early, which is already remarkable. But Webb's data suggested something more developed than expected. The galaxy appeared to be over 1,600 light-years across. That is small, compared with the Milky Way, which spans more than 100,000 light-years, but huge for such an early time. The light seemed to come mostly from young stars, rather than being dominated by the glare of gas near a growing supermassive black hole. The amount of starlight implied a mass of several 100 million suns. Then came the chemical surprise. Webb's mid-infrared observations indicated bright emission lines from hydrogen and oxygen. Later observations with ALMA added even more weight to the oxygen story. Oxygen in such a distant galaxy means that massive stars had already lived and died before the time at which we are seeing it. That is the part that makes the discovery feel almost uncomfortable. For oxygen to be there, the galaxy needed a past. Not a long past by modern standards, but enough time for gas to collapse, stars to ignite, nuclear fusion to build heavier elements, stars to end their lives, and enriched material to spread through the galaxy. All of that had to happen inside a universe less than 300 million years old. The question is not simply, how could a galaxy exist? It is, how could a galaxy already have a story? This is where the phrase "could change the universe" becomes more than a title. The universe itself is not changing because Webb found this object. The galaxy was always there, sending its light across time long before Earth had oceans, continents, forests, cities, or telescopes. What changes is our understanding. The mental map shifts. The timeline tightens. The models that seemed comfortable now have to explain a universe that may have become structured earlier and faster than expected. To see why that matters, we need to walk through what the standard picture said should happen after the Big Bang. Not the cartoon version, not the idea of an explosion into empty space. The real picture begins with an extremely hot, dense state. Space expanded. The universe cooled. In the first minutes, light elements formed. Hydrogen and helium dominated, with only tiny traces of lithium and related light nuclei. For a long time, the universe was a plasma through which light could not travel freely. Electrons scattered photons over and over, turning space into a glowing fog. Then, after hundreds of thousands of years, the universe cooled enough for electrons and nuclei to combine into neutral atoms. Light could finally move through space. That ancient light is now stretched into the cosmic microwave background, the oldest light we can observe. After that came darkness. Not because there was nothing. Matter existed, gravity existed, dark matter existed, hydrogen and helium filled the cosmos. But stars had not yet ignited. Galaxies had not yet assembled. The universe had become transparent, but there were no ordinary sources of light to illuminate it. These were the cosmic dark ages. In that darkness, structure grew slowly from small beginnings. Dark matter halos formed, merged and deepened. Gas fell into them. The first stars appeared. Their radiation changed the gas around them. Their deaths enriched the universe. Gradually, small galaxies formed, merged, and grew. This sequence makes sense, but every step requires time. Gravity needs time to gather matter. Gas needs time to form. Chemical enrichment needs time to happen. Galaxies need time to become bright and structured. When Webb finds a galaxy like JADES GS Z140, so early it does not merely add one dot to a catalog. It presses on all of those steps at once. Maybe gas cooled faster than expected. Maybe star formation was more efficient. Perhaps the earliest stars formed in bursts stronger than our models predicted. Dark matter halos may have assembled earlier in rare regions. Black holes could have added light to some objects, confusing mass estimates. Dust and chemical enrichment might have happened quickly through massive stellar explosions. Or the simulations may be missing physics that becomes crucial only under the extreme conditions of cosmic dawn. Each possibility is reasonable, none is simple. The early universe was denser than the universe today. A denser environment can change how gas behaves. Collisions, mergers, and inflows may have been more common. Fresh material could have streamed into small galaxies rapidly. If star formation was unusually efficient, then galaxies might have built stars faster than expected, without requiring the Big Bang itself to be wrong. That is an important distinction. The drama is real, but it has to be aimed correctly. The Big Bang theory says the universe was once hotter and denser, and has been expanding and cooling. It does not contain a perfect, final, unchangeable recipe for exactly how every early galaxy must grow in detail. Galaxy formation is a complicated field layered on top of cosmology. It involves gravity, gas, dark matter, radiation, chemistry, feedback, black holes, and messy, nonlinear physics. So when a galaxy appears too early or too bright, the first thing scientists question is usually the galaxy formation model, not the entire Big Bang. Still, there is a reason the headlines keep returning to the Big Bang, because the earliest galaxies sit near the beginning of the whole cosmic story. If enough of them are too massive, too common, too luminous, or too chemically evolved, then the pressure moves upward. It can begin to touch assumptions about dark matter, the rate at which structure grows, the first stars, the expansion history, and the initial conditions of the universe. A single discovery can be explained. A pattern is harder to ignore. That is why Webb's early results matter so much. JADES GS Z140 is not alone in raising questions. Webb has found many galaxies in the first few 100 million to billion years that appear surprisingly bright or mature. Some early candidates later turned out to be less extreme than first thought. Some were affected by black holes, dust, or measurement uncertainty. That is normal. Science corrects itself as better data arrives. But even after the corrections, the sense of surprise did not vanish. The early universe still looks busy. It looks productive. It looks capable of building bright galaxies quickly. It looks less empty, less slow, and less simple than many expected before Webb opened its infrared eyes. This is not a failure of science. It is science working at the edge. A model makes predictions. A better instrument gathers deeper evidence. The evidence agrees in some places and strains in others. Researchers adjust the model, reject wrong interpretations, test alternatives, and look again. The universe does not care which version of the theory made us comfortable. It simply sends the light. The challenge is reading it correctly. JADES GS Z140 is especially important because its distance is not based only on a guess from color. Webb obtained spectroscopic evidence. The Lyman alpha break in its spectrum allowed scientists to measure its redshift more securely. Later, oxygen detections helped refine the picture further. This matters because the most dramatic early universe claims often depend on whether the distance is real. A photometric redshift is useful, but it is not final. A spectroscopic redshift is much stronger. Think of it like seeing a shadow through fog versus reading a name written on the object itself. The shadow may tell you something is there. The name confirms what it is. Webb's spectrum gave JADES GS Z140 a place in time. And that place was astonishingly early, less than 300 million years after the Big Bang. The universe had already produced a galaxy whose starlight was powerful enough to cross almost all of cosmic history and still be detected by an observatory near Earth. That fact alone is enough to change the emotional scale of the beginning. The first chapters of the universe may not have been quiet pages of slow preparation. They may have been crowded, intense, and efficient. Galaxies may have started assembling in rare regions with shocking speed. Stars may have formed in dense bursts. Supernovae may have enriched their surroundings rapidly. Black holes may have grown early, feeding inside compact galaxies and altering what we see. And if that is true, then the first few 100 million years were not a waiting room. They were a factory. To understand the tension, imagine trying to build a city from raw material with almost no time. First, the land has to collect. Then the roads must form, power systems need to appear, buildings rise, factories start producing supplies. Some structures collapse and are rebuilt. Neighborhoods merge, waste is recycled into new construction. Somehow, when an observer arrives almost immediately after the process begins, the city is already glowing. That is the feeling astronomers get from JADES GS Z140. The raw materials were simple. The time was short. The result was not supposed to look this developed. Yet, there it is, a galaxy at the edge of time, carrying evidence that nature may have found a faster path. One possible path involves star formation efficiency. In the modern universe, turning gas into stars is not easy. Gas clouds resist collapse in many ways. They heat up as they compress. Radiation pushes back. Magnetic fields matter. Exploding stars inject energy into their surroundings. Newly formed stars can blow gas away before it turns into more stars. The process is often inefficient. But the early universe was different. Gas was denser. Galaxies were smaller. Dark matter halos were growing quickly. Streams of cold gas may have fed young systems rapidly. In some environments, the usual brakes on star formation may not have worked the same way. If early galaxies converted gas into stars more efficiently than expected, then they could become bright without violating the basic Big Bang framework. Another possibility involves the first stars themselves. If the earliest stars were, on average, much more massive than stars today, they would shine intensely and die quickly. Massive stars produce heavy elements and explode after only a few million years. That means chemical enrichment can happen fast. A small number of enormous stars could change the gas around them dramatically in a short time. This could help explain why oxygen appears so early. But it also creates new questions. How common were those massive stars? How quickly did they form? How much material did they return to their galaxies? Did they leave behind black holes that helped seed later growth? Were their explosions strong enough to blow gas out, or did dense early environments trap and recycle the material? Every answer opens another door. Black holes provide a different route through the problem. Some early galaxies may look brighter or more massive because a growing black hole at the center is feeding on gas. As material spirals inward, it heats up and shines. That light can make the galaxy appear more powerful than its stars alone would suggest. This has already helped reduce some of the early tension with the most extreme Webb candidates. But JADES GS Z140 is not easily dismissed as only a black hole trick. The observations suggest much of its light comes from young stars. That makes the problem more direct. The galaxy was not simply a hidden engine wearing a stellar mask. It seemed to contain a real young stellar population, bright enough to matter. A third possibility is that we are seeing rare peaks in the cosmic landscape. The universe is large. Even if most regions developed slowly, some unusually dense regions could have collapsed earlier. Webb's deep surveys may be finding rare places where structure formation ran ahead of average. A rare object does not necessarily break a theory. It tests how well the theory predicts the extremes. This is why the number of such galaxies matters. One unusually bright early galaxy can be a lucky outlier. 10 can still be explained with careful statistics. But if surveys keep finding more and more luminous galaxies at very high redshift, then the models must allow them naturally. They cannot remain permanent surprises. That is why astronomers care about luminosity functions. A luminosity function is a way of counting how many galaxies exist at different brightness levels during a particular era. It is not as emotionally dramatic as saying, a galaxy that should not exist, but it is more powerful scientifically. It tells us whether the universe is producing too many bright galaxies compared with predictions. JADES GS Z140 matters not only because it is distant, it matters because its brightness suggests that luminous galaxies may exist in the very early universe more often than expected. If that pattern holds, then models of early galaxy formation must change. Perhaps star formation started earlier. Perhaps it was more efficient. Maybe feedback behaved differently. Maybe dark matter halos grew in ways our simulations undercounted. Something in the recipe needs adjustment. This is the real story beneath the clickbait. Not Webb destroyed the Big Bang overnight. Something more interesting. Webb may be revealing that the universe became complex faster than we knew how to explain. That sentence is quieter, but it is more profound, because complexity is the bridge between the beginning and us. Hydrogen and helium alone do not make planets, oceans, bones, blood, forests, metal, or mines. Heavy elements are needed. Stars must form and die. Galaxies must gather and recycle material. The early universe has to move from simple physics to structured chemistry. Every surprising early galaxy tells us that the machinery of complexity may have switched on sooner than expected. JADES GS Z140 is not just a remote object. It is evidence that the universe began building the ingredients of later cosmic history with startling speed. Even oxygen at that distance carries a strange emotional weight. On Earth, oxygen is tied to breath, water, rock, life, and biology. In the early universe, it was not a sign of life. It was a sign of stellar death. It meant massive stars had already transformed simple matter into heavier elements and returned some of that material to space. In other words, the young universe had already learned how to recycle. That makes the discovery feel less like a single point of light and more like a compressed biography. Gas fell inward. Stars ignited. Light poured out. Massive stars died. Oxygen appeared. The galaxy kept shining. Its light began a journey longer than the future history of our entire solar system so far. Then, billions of years later, a species on a small rocky planet built a golden telescope, unfolded it in space, cooled it behind a sunshield, and caught that ancient signal. This is why Webb's discoveries feel different from ordinary astronomical measurements. They are technical, but they are also personal. They change the way we imagine the darkness before everything familiar existed. Before Webb, it was tempting to think of the first few 100 million years as a slow fade-in. First darkness, then a few stars, then tiny galaxies, then gradually larger systems. A calm dawn spreading over a mostly empty cosmic landscape. The new picture may be sharper. Dawn may have been explosive in certain places. Not explosive like the Big Bang itself, but explosive in the sense of rapid structure, fierce star formation, and chemical change. The first galaxies may not have been merely small candles. Some may have been furnaces. That matters for reionization, one of the great transitions in cosmic history. After recombination, neutral hydrogen filled the universe. Starlight could not travel freely through all of space in the way it does today because neutral hydrogen absorbed certain ultraviolet photons. Eventually, radiation from the first stars, galaxies, and possibly black holes ionized much of this hydrogen again. This period is called the Epoch of Reionization. By about 1 billion years after the Big Bang, the universe had largely become transparent to the kind of light that fills galaxies today. But the exact timing and sources of reionization remain major questions. If bright galaxies were already common very early, they may have contributed more ionizing radiation than expected. If young galaxies were efficient at forming massive stars, they may have helped clear the cosmic fog sooner or in a more patchy pattern. A galaxy like JADES GS Z140 may be one piece of that larger puzzle. This is why the discovery is not just about one galaxy's age. It touches the transformation of the entire universe. A bright early galaxy tells us about stars. Its oxygen tells us about chemical enrichment. Its redshift tells us about time. Its abundance, if many similar objects are found, tells us about the growth of structure. Its radiation may tell us about how the universe became transparent. Each clue connects to another. The deeper Webb looks, the more the beginning stops being a smooth diagram and becomes an active environment. That is both exciting and dangerous for old assumptions. For decades, cosmology has had a powerful standard model. It includes ordinary matter, dark energy, an expanding universe, and initial conditions inferred in part from the cosmic microwave background. This model has been extraordinarily successful. It explains the broad structure of the cosmos, the pattern of ancient background radiation, and the large-scale distribution of galaxies. But success on large scales does not mean every detail is finished. The formation of the first galaxies sits at the boundary between cosmology and astrophysics. The broad universe may be described well, while the smaller, messier processes inside early dark matter halos remain uncertain. Webb operates exactly at that boundary. It does not simply ask, did the universe begin hot and dense? It asks, how quickly did the first complexity arise inside that universe? And that is a harder question. Computer simulations try to answer it by combining gravity, gas physics, radiation, star formation, feedback, and chemistry. But simulations require assumptions. They cannot track every atom across the observable universe. They use approximations for processes that happen below the resolution of the model. Those approximations can work well in familiar regimes and fail in extreme ones. The first few 100 million years were an extreme regime. The gas was more pristine. The densities were higher. The radiation fields were different. The first stars may have had unusual masses. The earliest black holes may have grown under conditions we do not fully understand. So Webb is not merely taking pictures. It is stress testing the simulations. Some will survive with adjustments. Others will need deeper changes. A few assumptions that once felt reasonable may become obsolete. That is what a great telescope does. It does not flatter our theories. It exposes their weak edges. JADES, GS Z14. 0 is one of those edges. Consider the problem of time again. Less than 300 million years after the Big Bang sounds like a long time only because human lives are short. In galaxy evolution, it is a blink. Our Milky Way built its stars over billions of years. Large galaxies grow through mergers, gas inflow, bursts of star formation, and long periods of recycling. The first galaxies had to start from simpler conditions and do something dramatic very quickly. If JADES, GS-Z140 had several hundred million solar masses in stars, then enormous amounts of gas must have collapsed and converted into stars early. If oxygen was already present, massive stars must have lived and died. If dust reddened some of the light, even more processing may have occurred. The young universe was not supposed to waste time, but this is still astonishing. A useful way to think about it is not that the galaxy is impossible. The better word is demanding. It demands high efficiency. It demands early collapse. It demands rapid enrichment. It demands a set of physical conditions that may be rare, extreme, or poorly represented in older models. Science often advances when the universe makes demands. Mercury's orbit demanded a better theory of gravity. The cosmic microwave background demanded a hot, early universe. The accelerating expansion demanded dark energy, or something acting like it. Now Webb's early galaxies may be demanding a better theory of how the first luminous structures formed. That does not make the Big Bang useless. It makes the beginning more complicated. And the complication is the point. The public often hears theory and thinks it means a fragile guess. In science, a strong theory is more like an interconnected structure. It can contain pieces that are extremely well supported and pieces that are still being refined. The Big Bang framework is supported by deep evidence, but the timeline of early galaxy growth is still an active field. Webb is pushing directly into that active field. The telescope's discoveries do not invite us to throw away everything. They invite us to ask which parts of the story were too simple. Maybe we underestimated the speed of early star formation. Maybe the first galaxies were more efficient because gas was denser and easier to trap. Perhaps massive stars formed in ways that produced light and oxygen faster than expected. Maybe black holes were common enough to complicate our measurements. Possibly rare regions of the universe collapsed earlier than the average models suggested. A more radical possibility is that the background cosmology itself may need subtle changes. Some researchers explore ideas such as early dark energy, modified dark matter behavior, or different initial conditions. These are not accepted replacements for the standard model, but they show how seriously scientists take the tension. If the data eventually demands deeper changes, cosmology will follow. For now, the safer and more accurate statement is this: James Webb has not killed the Big Bang. It has made the young universe harder to explain. And sometimes that is how revolutions begin. Not with a theory falling instantly, not with one observation destroying a century of evidence, but with a small mismatch that refuses to disappear. At first, the mismatch looks like an exception. Then, another appears. Instruments improve. Errors are removed. The remaining tension becomes sharper. Scientists try ordinary explanations. If those fail, the deeper framework starts to bend. No one knows yet whether Webb's early galaxies will lead that far. But the possibility is why the story matters. The discovery sits at the edge of what we know, where responsible science and real wonder overlap. It is tempting to imagine JADES, GS-Z140, as a single ancient island, alone in the cosmic dark. But Webb's surveys suggest the young universe may contain many such islands. Some are fainter, some are redder, some may hide active black holes, some may be magnified by gravitational lensing, some will disappear from the most extreme lists after better data. Others will become even more remarkable. The catalogue is still growing. With every new field, astronomers refine the count. They ask how many galaxies existed at each redshift, how bright they were, how large they were, how much stellar mass they contained, and how rapidly they formed stars. The answer is not one object. It is a distribution. And distributions are where cosmology becomes unforgiving. A theory can shrug at one outlier. It cannot shrug forever at a population. If the early universe produced too many bright galaxies, then something real must explain them. Either the measurements are wrong, the astrophysics is incomplete, or the cosmological assumptions need adjustment. Those are the choices. This is why the James Webb story is still unfolding. The first wave of headlines was messy. Some claims were exaggerated. A few early candidates became less threatening once more data arrived. NASA itself has reported work showing that some early galaxies were not as massive as first thought, because black holes can add extra brightness. That reduced the sense of immediate crisis. Yet the mystery did not end. Even after removing the most misleading objects, astronomers still see signs that the early universe was producing galaxies faster or more efficiently than expected. The question shifted from, "Is the universe broken?" to, "What did the early universe know how to do that? Our models did not." That is a better question. It leads to physics. It leads to gas. It leads to stars. It leads to dark matter halos and radiation fields and chemical enrichment. Most of all, it leads back to time. Because time is the pressure behind the entire discovery. If JADES, GS-Z140, had existed 2 billion years after the Big Bang, it would still be interesting, but not shocking in the same way. If it appeared 1 billion years after the Big Bang, it would be part of a growing early galaxy story. But less than 300 million years changes the emotional meaning. It pushes the object toward the first chapter. It asks how quickly the universe moved from mere simplicity to luminous structure. To see that properly, imagine reversing cosmic history. The present universe fades backward. Galaxies move closer in time. The sun disappears. The Milky Way becomes younger, more chaotic, less settled. Heavy elements become rarer. Planets vanish from the story. Generations of stars are removed. Galaxies shrink, merge, and simplify. Eventually, we approach an era when most of the familiar cosmic architecture has not yet formed. Then, near that darkness, Webb finds a galaxy already shining. Not fully grown, not like the Milky Way, not mature in the modern sense, but too bright to ignore. It is like finding a lit window in a city that was supposed to still be under construction. The more we learn about that window, the stranger it becomes. Its redshift places it near the beginning. Its size shows that the light is spread across a real stellar system. Its brightness implies rapid growth. Its oxygen suggests chemical evolution had already begun. Its existence hints that other bright galaxies may be waiting beyond current limits. This is why Webb may change the universe in our minds. Not by moving the stars, by moving the beginning. The beginning may have been brighter, earlier, faster, more complex, and if that is true, the first 500 million years of cosmic history must be rewritten with more urgency. One of the hardest parts of this story is that the distant universe does not offer easy visual drama. JADES, GS, Z14, does not look like a majestic spiral in a colorful poster. It does not have sweeping arms, a bright central bulge, or a glowing disk you can admire in the ordinary way. To the eye, it is a faint, stretched, reddish feature. Its power comes from context. Without the redshift, it is a smudge. With the redshift, it becomes a messenger from the edge of time. This is true of much of modern astronomy. The most important objects are not always the most beautiful in the obvious sense. Sometimes, the universe hides its deepest messages in the faintest data. A dip in a spectrum, a missing color, a line of oxygen, a brightness too high for comfort. The drama is not in the image alone. It is in what the image means. That is also why Webb's early galaxies are difficult to explain to the public without oversimplifying. Saying this breaks the Big Bang is dramatic, but misleading. Saying this challenges certain models of early galaxy formation under the standard cosmological framework is accurate, but almost no one clicks it. The truth sits between those extremes. The Big Bang is not dead, but the early universe is no longer behaving like the simple version many people imagined. Webb has shown that galaxies may have appeared, grown, and enriched themselves with surprising speed. That does not erase the Big Bang. It sharpens the mystery of what happened after it. The difference matters because good science needs precision, while good storytelling needs tension. This video needs both. The tension is real. A universe less than 300 million years old should not have had much time to create a luminous, chemically interesting galaxy. And yet the evidence points to exactly that. So the responsible question is not, was there no Big Bang, but what kind of Big Bang universe produces galaxies this quickly? That question is deeper than a simple denial. It keeps the evidence and expands the mystery. To answer it, astronomers must understand how the first stars formed. They need to know whether early stellar populations were top-heavy, meaning they produced more massive stars than modern star-forming regions. Massive stars could flood young galaxies with ultraviolet light, explode quickly, and seed the gas with oxygen and other elements. They also need to understand feedback. Feedback is the way stars and black holes push back on their surroundings. A burst of star formation can heat gas, drive winds, and stop further star formation. But it can also compress nearby gas and trigger new stars. A growing black hole can blast radiation outward, but it can also reveal itself as a bright source that changes how we estimate a galaxy's mass. In early galaxies, feedback may have been fierce and rapid. A small galaxy could flare with star formation, enrich itself, lose gas, regain gas, and flare again. Instead of smooth growth, the first galaxies may have lived in violent cycles. A galaxy observed during one bright phase could look surprisingly luminous for its age. JADES GSZ14 0 may be one of these intense early systems, or it may represent a broader class of galaxies that our models underproduced. That distinction is crucial. If it is rare, it tells us about the extremes. If it is common, it rewrites the average story. Webb is still gathering the evidence needed to decide. Another clue comes from size. The galaxy's light appears spread over a region more than 1,000 light-years across. That is not enormous by later cosmic standards, but it suggests a real galaxy-scale structure, rather than a single compact point. In the early universe, size is not just geometry. It tells us how matter had already organized itself. A young galaxy needs a dark matter halo to gather gas. The halo must be massive enough for gas to cool and remain bound. Star formation must occur across enough material to produce the observed light. If the object is physically extended, then the process was not confined to a tiny spark. The system had already become a place. That idea is strangely important. A place, in cosmic terms, means gravity had drawn boundaries. Gas had gathered. Stars had formed within a shared environment. Chemistry had begun to change that environment. The universe had moved beyond scattered particles and into architecture. Architecture before 300 million years. This is the shock. The cosmic microwave background shows us the universe at about 380,000 years after the Big Bang, when it became transparent. That image is astonishingly smooth, with tiny fluctuations that later grew into galaxies. JADES GSZ14 0 appears less than 300 million years after the Big Bang, after those tiny fluctuations had somehow become a luminous galaxy. Between those two moments lies the transformation Webb is now beginning to reveal, from faint ripples to stars, from darkness to galaxies, from hydrogen and helium to oxygen, from a nearly smooth universe to the first visible structures. That transformation used to be mostly theoretical. Now it is becoming observational, and observations are less polite than theories. They show what happened, not what should have happened. The question then becomes unavoidable. Were our expectations too slow? For years, many models predicted that the first galaxies would be small and faint. That was not foolish. It followed from the idea that structure grows hierarchically, with small things forming first and merging into larger things over time. Gravity amplifies density fluctuations, but building mass takes time. Early galaxies should exist, but the brightest and most massive systems should be rare. Webb did find faint galaxies, but it also found bright ones. The surprise is not that any galaxies existed early. The surprise is how much some of them had already achieved. This is why the phrase, "too early," keeps appearing in discussions of Webb discoveries. Too early does not mean physically impossible. It means earlier than the most comfortable version of the model expected. The universe is allowed to surprise us. The model is the thing that must adapt. Still, adaptation can take many forms. The most conservative path says the standard cosmological model remains intact, but the astrophysics of early star formation needs revision. Under this view, early galaxies formed stars more efficiently, produced more light per unit mass, or went through bursty phases that made them easier for Webb to detect. A second path says measurement effects explain part of the tension. Some objects may contain active black holes. Some may have unusual dust properties. Some may be magnified by gravity. Some photometric candidates may sit at lower redshift than first believed. Better spectra will sort them out. A third path leaves the door open to deeper changes. If future surveys find too many confirmed, massive, chemically evolved galaxies at extremely high redshifts, then cosmologists may need to revisit assumptions about the growth of structure itself. That could involve dark matter, early dark energy, primordial fluctuations, or other physics not yet fully understood. No responsible scientist jumps to the third path first, but no responsible scientist rules it out forever. This is the balance Webb has created. Caution and excitement at the same time. The discovery is strong enough to matter, but not simple enough to turn into a slogan. That is why the first half of this journey must stay grounded. We need the wonder, but we also need the discipline. JADES GSZ140 is not a magic bullet against cosmology. It is a demanding clue from cosmic dawn. The universe is telling us, look again. And when we look again, the beginning becomes stranger. One of the most remarkable things about this galaxy is that Webb found it in a relatively small region of sky. The observable universe is vast, and deep surveys cover only tiny windows at a time. If such a luminous galaxy appears in one small search area, astronomers naturally ask how many more exist elsewhere. That question can change everything. If JADES GSZ140 is a lucky rare object, then it marks the extreme edge of early galaxy formation. But if it is the first obvious member of a larger hidden population, then the early universe was far more active than expected. Future Webb surveys, combined with ALMA and eventually other observatories, will help decide which picture is right. The search will not be easy. At these distances, galaxies are faint, small, and redshifted into wavelengths that require long observations. Spectroscopy takes precious telescope time. Confirming one galaxy can require hours of exposure and careful analysis. Each new record comes with uncertainty, debate, and revision. But the direction is clear. Astronomers are no longer only asking when the first galaxies appeared. They are asking how quickly those galaxies became powerful. That word, powerful, includes more than brightness. It includes the ability to form stars, enrich gas, ionize surroundings, grow structure, and survive feedback. A galaxy at cosmic dawn is not merely a collection of stars. It is a machine that changes its environment. JADES GSZ140 seems to have been such a machine very early. That is why oxygen matters so much. The first stars began with simple fuel, hydrogen fused into helium. Later stages in massive stars created heavier elements. Supernovae and stellar winds returned those elements to the surrounding gas. New stars could then form from enriched material. Over billions of years, this cycle made the chemical universe we know. Seeing oxygen when the universe was so young means that part of the cycle had already happened. The young universe was not chemically frozen. It was evolving. Fast. This raises a subtle but powerful possibility. Maybe the first galaxies did not wait for many slow generations to enrich themselves. In the densest early environments, a handful of massive stellar generations may have changed the chemistry quickly. If those stars were huge and short-lived, their deaths could seed oxygen on timescales of only a few million years. That helps. But it also implies intense star formation before the observed moment, so the galaxy's visible age may not be the beginning of its story. If oxygen was already present, then the first stars inside or around that system must have formed earlier than the moment Webb sees. This pushes activity even closer to the Big Bang. That is one reason the discovery feels so profound. The galaxy is observed at less than 300 million years. Its preparation began before that. The universe had to start building the conditions for this object even earlier, perhaps when the cosmic dark ages were only beginning to end. This is where the timeline tightens almost painfully. 380,000 years, the universe becomes transparent. Then darkness. First stars, uncertain timing. First galaxies, uncertain growth. Less than 300 million years. JADES, GS-Z14. Zero is already shining, extended, luminous, and chemically interesting. The gap is not empty, but it is short. Everything important had to happen inside it. Gravity had to amplify structure. Dark matter halos had to assemble. Gas had to fall in and cool. Stars had to form. Some stars had to die. Elements had to spread. The galaxy had to become bright enough for Webb to detect. That is the challenge. Not one impossible miracle, a whole chain of fast events. Every link in that chain can be studied, but none is trivial. Change the efficiency of cooling, and the timeline shifts. Change the mass of the first stars, and the light changes. Change feedback and gas retention changes. Change the abundance of early halos, and the number of bright galaxies changes. Change black hole growth, and mass estimates change. The discovery sits at the intersection of all those uncertainties. That is why it could change our view of the universe. It is not because the galaxy is large in the sky. It is not because the image itself is visually overwhelming. It is because the object touches the hidden machinery between the Big Bang and the first recognizable galaxies. For a long time, that machinery was mostly inferred. Now, Webb is beginning to observe it directly. A telescope built by humans is studying the universe at an age when no planets like Earth existed. No metal-rich stars like the Sun had formed, and no life could have looked back. This is one of the deepest forms of time travel available to science. But it comes with a strange limitation. Webb can see ancient light, but it cannot pause the universe and watch the galaxy evolve. Each distant galaxy is a snapshot. To reconstruct the story, astronomers must compare many snapshots at different redshifts, like scattered pages from a book, with most of the chapters missing. JADES, GS-Z140 is one page. An extraordinary page, but still only one page. The surrounding chapters must be found elsewhere, in fainter galaxies, in slightly later systems, in chemical measurements, in simulations, and in the cosmic microwave background that records the seed fluctuations from which everything grew. That is why Webb's work is not finished by breaking a distance record. The record is only the doorway. Beyond it lies the harder question. What kind of universe produces that record? A useful way to frame the mystery is to separate three things that people often mix together. First, there is the Big Bang framework. The universe began in a hotter, denser state and has expanded and cooled over time. Second, there is the standard cosmological model, a more detailed picture involving ordinary matter, dark energy, expansion history, and initial fluctuations. Third, there are models of galaxy formation, the messy astrophysics of how gas turns into stars and galaxies inside dark matter halos. Webb's early galaxies mainly challenge the third layer. They may also pressure the second layer if the population becomes too extreme. They do not automatically destroy the first layer. This distinction protects the science from hype, but it does not make the discovery boring. In fact, it makes it more interesting, because it shows exactly where the unknowns live. The Big Bang may still describe the broad beginning. The open question is, how quickly that beginning became rich enough to make galaxies like this. If the answer requires only better star formation physics, that is still a major advance. If it requires different assumptions about early structure, the implications become larger. If it eventually points toward new cosmology, then Webb will have done something even more extraordinary. At the moment, the honest answer is unresolved. and unresolved is where the wonder lives. A settled universe is easy to narrate. An unsettled universe is alive. But Webb is not finished with that unsettled universe. The next step is to follow the evidence into the more dangerous part of the question. If one early galaxy can be explained by rare conditions, what happens when more of them appear? If oxygen, dust, bright starlight, compact black holes, and rapid growth keep showing up near cosmic dawn, the mystery stops belonging to one object and begins to belong to the entire young cosmos. That is where the story becomes much larger. In the second half, we will look at what these early galaxies might really mean for the Big Bang, which explanations are most likely, which ones are more radical, and why James Webb may be showing us that the first light in the universe was not a slow beginning at all. It may have been the first sign that the universe learned how to build complexity almost immediately. That idea changes the way the discovery should be understood. This is not only a story about one ancient galaxy sitting at the edge of what our telescopes can see. At its center is speed. How quickly can nature move from an almost smooth early universe to something structured, bright, chemically active, and complex? How fast can gravity gather matter? How quickly can stars turn simple hydrogen and helium into oxygen, carbon, and dust? How early can black holes appear, and how much can they change what a young galaxy looks like from across cosmic time? JADES GS-Z140 forces those questions into a very narrow window. A young universe does not have the luxury of billions of years. At roughly 290 million years after the Big Bang, almost every process has to be fast. Gas has to collapse fast. Stars have to form fast. Massive stars have to live and die fast. Heavy elements have to spread fast. Light has to escape through surrounding gas fast enough for Webb to see it. That does not mean the Big Bang is suddenly wrong. A more careful statement is much more interesting. The broad Big Bang picture still has enormous evidence behind it. The universe expands. Distant galaxies show redshift. The cosmic microwave background fills the sky as ancient cooled radiation. The light elements follow patterns expected from a hot, dense, early phase. Webb has not erased those pillars. Instead, Webb has aimed directly at a younger and messier layer of the story. The problem is not whether the universe began hot and dense. The sharper question is how that beginning became organized so quickly. That difference matters, because the phrase Big Bang Theory is often used as if it means one single idea. In reality, it is a stack of ideas. At the base is the hot, expanding early universe. Above that sits the standard cosmological model, with dark matter, dark energy, ordinary matter, radiation, and the growth of structure from tiny initial fluctuations. Above that sits the astrophysics of galaxy formation, where gas cooling, turbulence, star birth, supernova explosions, dust, black holes, and feedback all collide inside simulations. A discovery can shake the upper layers without destroying the foundation. That is probably where the Webb discoveries are doing their work. They are not simply saying, the beginning never happened. They are saying the beginning may have been more productive than expected. Galaxies may have become bright more efficiently. Stars may have formed in bursts more violently. Black holes may have contributed to the light earlier than we assumed. The first heavy elements may have appeared and circulated faster than our comfortable timelines allowed. In other words, the universe may not be older than we thought. It may have been better at building things. That possibility is unsettling in a different way. A slower, early universe is easier to imagine. First darkness, then a few stars, then small galaxies, then larger galaxies. Step by step, the cosmos grows into complexity over a vast amount of time. That picture feels natural because it resembles human construction. We lay a foundation, raise walls, add details, and only much later see the finished building. But nature is not required to build at human speed. The early universe may have been a more extreme environment than our simple mental picture allows. Gas was denser. Interactions were more common. Dark matter halos were assembling from the first gravitational seeds. Massive stars could burn through their fuel in only a few million years, die violently, and spread newly forged elements into their surroundings. A young galaxy could experience a burst so intense that for a brief cosmic moment, it looked far brighter than its long-term mass might suggest. Seen from 13 billion years away, that brief bright phase can be mistaken for something larger and more impossible than it really is. This is one of the first explanations scientists consider. Maybe some early galaxies are not impossibly massive. Maybe they are temporarily brilliant. Brightness and mass are related, but they are not the same. A small fire burning intensely can outshine a larger one that burns quietly. A young starburst galaxy can produce huge amounts of ultraviolet light if many hot, massive stars are forming at once. From a deep image, that galaxy may look like it contains far more stars than it actually does, unless spectroscopy and careful modeling reveal what is happening inside. Webb has made this distinction unavoidable. Before Webb, many of the earliest galaxy candidates were judged by their colors in images. Astronomers looked for a sharp drop in light at certain wavelengths, a sign that the galaxy was extremely distant. This method is powerful, but it is not final. Dusty, closer galaxies can sometimes imitate the colors of very distant galaxies. Unusual stellar populations can confuse simple assumptions. Without spectra, a candidate can remain a question mark. Spectroscopy turns that question mark into something stronger. By spreading a galaxy's light into its component wavelengths, Webb can search for features that reveal redshift, composition, star formation, and sometimes the influence of black holes. For JADES GS-Z140, the spectroscopic redshift made the distance real. It was not just a red dot in an image. It was confirmed ancient light. That confirmation is why the object matters so much. A candidate at the edge of the universe is exciting. A confirmed galaxy at the edge of the universe is a landmark. Once the redshift is secure, the easy escape routes disappear. The galaxy cannot simply be moved closer to make the problem go away. Its light really does belong to a time when the universe was only a tiny fraction of its present age. From that point forward, the question shifts from whether it is there to how it became what it is. Several answers are possible. The first is efficiency. Perhaps the earliest galaxies turned gas into stars more effectively than many models assumed. In the modern universe, star formation is often inefficient. Gas clouds do not instantly become stars. Magnetic fields, turbulence, heating, feedback from young stars, supernovae, and the motion of the galaxy all complicate the process. Much of the gas can remain diffuse, be blown out, or fail to collapse. Early conditions may have changed the balance. Dense gas in young halos might have formed stars in short, powerful bursts. If a galaxy converted a larger fraction of its available gas into hot stars quickly, it could become much brighter than expected without requiring a completely new cosmology. The basic universe would be the same, but the recipes inside the first galaxies would need revision. That kind of revision sounds small only if you underestimate galaxy formation. A galaxy is not a simple object. It is a living contest between gravity and pressure, cooling and heating, collapse and explosion, order and chaos. Change one part of that contest, and the whole young universe can look different. Imagine a dark matter halo gathering gas at cosmic dawn. Gravity pulls inward. Gas falls toward the center. As it compresses, it heats. To form stars, it must cool enough to fragment. If cooling becomes efficient, dense clumps can appear. Massive stars ignite. Their radiation pushes outward. Supernovae tear through the gas. Some material escapes, but some falls back. A black hole may grow in the middle, heating or illuminating its surroundings. Dust begins to form from the ashes of dead stars. New generations of stars inherit a slightly richer chemical environment. All of this can happen while the galaxy is still young. The second explanation involves the stars themselves. The first generations of stars may not have resembled the average stars forming today. In modern galaxies, many stars are small, cool, and long-lived. They add mass without adding overwhelming brightness. Massive blue stars are rarer, but they dominate a galaxy's light. If early galaxies formed a higher fraction of massive stars, they could shine with unexpected power for their size. Astronomers call this the initial mass function, the distribution of star masses at birth. A top-heavy initial mass function means more massive stars. More massive stars mean more ultraviolet light, faster chemical enrichment, and stronger feedback. They also die quickly. In only a few million years, some explode as supernovae, spreading heavy elements into the surrounding gas. That could help explain why signs of chemical maturity appear so early. This idea does not require the Big Bang to fail. It requires the first stellar nurseries to be different. Still, different is not a minor word here. If the first galaxies produced stars in a way unlike galaxies today, then many estimates of their mass, age, and evolution must be handled with greater caution. The early universe would not simply be a smaller version of the modern one. It would be a harsher, brighter, more unstable laboratory, where the usual rules still apply. But the conditions push them to extremes. A third possibility is dust. Dust sounds ordinary, but in cosmology it becomes one of the strangest characters in the story. Cosmic dust is not household dust. It is made of tiny grains of heavy elements formed inside stars and scattered by stellar winds or supernova explosions. In the early universe, dust should be limited because heavy elements need stars to produce them. Finding dust too early would imply that some stars had already lived, died, and enriched their environment. Dust can also hide star formation. A galaxy may be forming stars violently while much of its light is absorbed and re-emitted at longer wavelengths. Depending on what wavelengths we observe, a dusty galaxy can look older, redder, dimmer, or stranger than it truly is. Mid-infrared and sub-millimeter observations become essential because they reveal pieces of the story that near-infrared images alone cannot show. This is why Webb and ALMA together are so powerful. Webb sees the stretched starlight and spectral fingerprints from extremely distant galaxies. ALMA, observing at millimeter and sub-millimeter wavelengths from the Atacama Desert, can detect cold gas, dust, and specific emission lines that reveal chemical elements. When an early galaxy is studied by both, its story becomes less like a single photograph and more like a multi-instrument interrogation. JADES GSZ14. Zero became even more fascinating when oxygen was reported in its light. Oxygen is not primordial. It was not produced in large amounts during the earliest moments of the Big Bang. It is forged in stars and spread into space when massive stars die. Detecting oxygen in such a distant galaxy suggests that chemical enrichment had already begun surprisingly early. That fact does not mean the galaxy looked like the Milky Way. It means the first cycle of stellar life and death had already started. A star had to form. It had to live. It had to manufacture heavier elements. It had to die or shed material. Then, that enriched matter had to become part of the galaxy's observable environment, all before the universe was 300 million years old. That is the part that should make the listener pause. Not because oxygen is impossible there, but because oxygen is a clock. It tells us that earlier events must have happened before the moment we are observing. A young galaxy with oxygen is not at the beginning of its own story. It already has a past. The deeper Webb looks, the more often the first chapter seems to begin before the page we are reading. Another explanation points toward black holes. In the modern universe, supermassive black holes sit at the centers of many large galaxies. Some weigh millions or billions of times the mass of the Sun. When they feed on surrounding gas, the material heats up and shines intensely, creating an active galactic nucleus. From far away, that activity can make a galaxy look brighter and more compact than its stars alone would allow. If black holes were common in early galaxies, they could distort our interpretation. A young galaxy might appear too massive because some of its light is not coming from ordinary starlight. It might be partly powered by accretion around a black hole. The galaxy's colors, size, and spectrum might then mislead simple models that assume stars dominate the emission. Webb has found many strange compact red objects in the early universe, sometimes nicknamed little red dots. Some may contain active black holes. Others may be dense stellar systems wrapped in dust. The category is still being studied, but it has already taught astronomers a lesson. The early universe contains objects that do not fit neatly into the boxes built from nearby galaxies. That makes the first billion years harder to read. A point of light could be a galaxy, a black hole, a dense stellar population, a dusty system, or some mixture of all of them. The same object may change its appearance depending on the wavelength, the instrument, and the assumptions used to model it. A record-breaking galaxy is therefore not just a record. It is also a test of our methods. How do we know what we are seeing when we cannot resolve the object in detail? The answer is not one measurement. It is a network of clues. Size matters, color matters, spectral lines matter, the shape of the light across wavelengths matters, the surrounding field matters. Follow-up observations matter. Simulations matter, but only when they remain tied to data. A claim becomes stronger when multiple clues point to the same conclusion. That is why the strongest Webb discoveries take time. The public often sees a headline immediately. Galaxy breaks the Big Bang. Astronomers see a longer process. First comes detection, then candidate selection, then spectroscopy if possible, then mass estimates, then comparison with models, then independent analysis, then new observations. Along the way, some early claims weaken, some become landmarks. JADES GS Z140 belongs in the landmark category because its distance is spectroscopically supported and its properties are unusual enough to matter. Yet even here, caution remains part of the wonder. Science is not weakened by caution. It is made credible by it. A less careful video would say that James Webb has destroyed the Big Bang. That sounds dramatic, but it misses the deeper tension. The real drama is more precise. Webb may be showing that galaxy formation at cosmic dawn was faster, brighter, and more chemically active than many expectations allowed. That is not a small discovery. It touches the timeline of complexity itself. To see why, consider what the standard picture expected in broad terms. After the hot early universe expanded and cooled, atoms formed. The cosmos became transparent, but it did not immediately fill with stars. For a long period, the universe was dark, invisible light. Gravity slowly amplified tiny density variations, pulling matter into dark matter halos. Gas gathered in those halos. The first stars ignited. Their radiation began to change the surrounding hydrogen. Small galaxies merged and grew. Over hundreds of millions of years, the universe moved from darkness towards structure. Nothing in that outline is destroyed by Webb. The pressure comes from the pace. If large numbers of bright galaxies appear earlier than expected, then one or more ingredients must change. The seeds of structure may have been slightly different. Star formation may have been more efficient. Feedback may have allowed gas to remain and keep forming stars. Black holes may have contributed to brightness. Dust and emission lines may have affected mass estimates. Simulations may have missed rare but important pathways. Each option changes the story in a different way. The simplest pathway is better astrophysics. In this view, the universe itself is behaving according to the standard cosmological model. Dark matter builds halos. Ordinary matter falls in. The expansion history remains the same. The cosmic microwave background remains the same. What changes is the small-scale physics inside young galaxies. This would still be a revolution for galaxy formation. Models would need to produce bright, chemically enriched systems earlier. Simulations would need to capture bursty star formation, feedback cycles, rapid enrichment, and compact structures under extreme early conditions. The first galaxies would no longer be treated as faint, simple, fragile objects. Some of them would be recognized as intense engines capable of producing surprising amounts of light and chemistry in short bursts. A more ambitious pathway involves the dark matter halos themselves. Galaxies form inside halos of dark matter. Although dark matter does not shine, its gravity provides the scaffolding, where ordinary gas can collect. If halos massive enough to host bright galaxies are more common at very early times than expected, the problem becomes more cosmological. It might suggest that the initial fluctuations were arranged differently on small scales, or that the growth of structure happened in a way our models do not fully capture. This possibility is more serious. The cosmic microwave background gives us a snapshot of the universe when it was about 380,000 years old. Tiny temperature variations in that radiation are the seeds from which later structure grew. The Standard Model does an impressive job connecting those early fluctuations to the large-scale universe we see today. But the first galaxies live on relatively small scales, and at very early times, where direct observational tests were limited before Webb. Webb has opened that missing arena. If observations eventually show that early bright galaxies are far too common for the Standard Model, not just individually surprising, then the pressure moves downward in the stack. It begins to touch assumptions about how structure grows. That would not automatically erase the Big Bang, but it could force adjustments to the details of cosmology. For now, the evidence is not that extreme. Some early claims of galaxies being impossibly massive have softened as better data arrived. In several cases, light from active black holes, dust, or different stellar populations reduced the tension. NASA has described work showing that when certain compact red sources are removed or reinterpreted, the remaining early galaxies can fit much better within the Standard Model. The crisis becomes less like a broken universe and more like a warning that the first analysis was too simple. That warning is valuable. The first look at a new frontier is often misleading. When Hubble first revealed the deep universe, it changed the scale of what could be observed. Webb has done something similar for cosmic dawn. It is not surprising that the earliest interpretations were unstable. Astronomers were suddenly seeing objects in a regime that had never been studied this well. Still, the surprises have not disappeared. Even after corrections, the young universe seems unusually productive. There may be more bright galaxies than expected. Some show signs of rapid enrichment. Others appear compact, red, or strangely mature. The details vary, but the overall message remains. The first few 100 million years were not quiet. That matters because cosmic dawn was supposed to be the transition between simplicity and complexity. Before stars, the universe was mostly hydrogen, helium, dark matter, radiation, and gravity. No rocky planets, no oxygen-rich atmospheres, no carbon chemistry in the way life would eventually use it. Stars changed that. Galaxies organized that change. Every heavy element in our bodies was made possible by stellar generations that began somewhere in the early universe. When Webb finds evidence that enrichment started very early, it is not only changing a timeline on a chart, it is pushing back the beginning of cosmic complexity. The phrase could change the universe does not mean the telescope physically changes anything. The universe has already lived its history. What Webb changes is the human version of that history. It forces our timeline to make room for faster growth, earlier light, and perhaps stranger first structures than we expected. This is why JADES GS Z140 is more than a distance record. Distance records are easy to misunderstand. A new farthest galaxy appears. People admire it for a moment and then wait for the next record to replace it. But the record itself is not the main point. The real question is what kind of universe allows a record like that to exist with these properties. A tiny, dim, chemically primitive object at that redshift would still be extraordinary. A bright, extended, chemically interesting galaxy is different. Activity is built into the signal. A hidden past must come before the observed moment. By the time Webb sees it, the mechanisms of galaxy birth were already running hard near the beginning. One way to make sense of this is to imagine cosmic history as a dark landscape, slowly filling with fires. The old picture suggested the first fires were rare and faint, with darkness dominating for a long time. Webb is finding that some of those first fires may have burned fiercely. They may have formed in dense pockets, fed by gas streams, and flared brightly enough to be seen across nearly all of time. The darkness was real, but it may not have been as empty as we imagined. Another important piece of the puzzle is reionization. After the universe became transparent, most hydrogen gas was neutral. This neutral gas could absorb certain kinds of ultraviolet light. When the first stars and galaxies formed, their radiation began stripping electrons from hydrogen atoms, gradually ionizing the gas between galaxies. This process, called reionization, transformed the universe. It did not happen everywhere at once. Bubbles of ionized gas likely grew around the earliest luminous sources. Over time, those bubbles expanded and overlapped until much of the intergalactic medium became ionized. The timing and sources of reionization remain major questions. Webb's early galaxies may be central to the answer. If galaxies like JADES GS Z140 were bright and active very early, they could have contributed to clearing the cosmic fog. Their ultraviolet light, if able to escape, would have helped ionize surrounding hydrogen. The number, brightness, and escape fraction of early galaxies therefore matter not only for galaxy formation, but for the transformation of the universe itself. In that sense, Webb is not just finding old galaxies. It is investigating how the universe became visible. The first light did not simply appear. It had to fight its way through gas. Stars had to form in sufficient numbers. Radiation had to escape from galaxies. Regions of ionized hydrogen had to grow. Every newly confirmed galaxy near cosmic dawn becomes a clue to that transition. JADES GS Z140 arrives at a time when reionization may have been beginning in local patches, but long before the process was complete. Its existence tells us that luminous sources were already present. Its chemical signs suggest prior stellar activity. Its brightness suggests that some early systems could be important contributors to the changing state of intergalactic space. That opens a larger question. Was the early universe dominated by many small galaxies, each contributing a little light, or by rarer bright systems that punched large holes through the surrounding hydrogen? Webb is beginning to weigh those possibilities. The answer affects how we understand the first billion years. A universe reionized mostly by countless faint galaxies would look different from one shaped by intense bursts, compact star factories, and active black holes. Both scenarios may be partly true. The difficulty is measuring galaxies that are often too faint to see directly, then inferring their combined effect on gas spread across cosmic distances. Here again, one object becomes part of a larger population. A single galaxy can inspire the question. The population decides the answer. This is why future surveys matter so much. Webb has already changed the frontier, but the frontier is still small. Deep fields cover tiny patches of sky. Rare objects can be missed or overrepresented. Cosmic variance, the natural unevenness of structure from place to place, can make one field look different from another. To know whether JADES GS Z140 is a rare extreme or part of a broader pattern, astronomers need more fields, more spectra, and more confirmed examples. That is where the next years become important. If future Webb observations find only a few galaxies like it, the explanation may focus on rare bursts and unusual conditions. If many similar objects appear, the models will feel greater pressure. The question will shift from how did this galaxy form so early to why did early galaxy formation work so efficiently across the universe? The difference is enormous. A rare object challenges details. A common population challenges the framework. The same logic applies to chemical enrichment. Oxygen in one galaxy is surprising, but can be explained by rapid local star formation. Oxygen and other heavy elements in many galaxies at similar times would imply that enrichment was widespread sooner than expected. That would revise the timeline for the first stars, the first supernovae, and the first cycles of matter through galaxies. Cosmic history would become more compressed, not shorter in age, but richer in activity per unit time. Compression is the hidden theme of Webb's early universe discoveries. Events that once seemed spread out may have overlapped. The first stars, first galaxies, first black holes, first dust, and first chemical enrichment may not have followed a neat sequence with long pauses between them. In dense regions, several stages may have happened almost on top of one another. That is difficult to model. Computers can simulate the universe, but the first galaxies involve processes across an enormous range of scales. Dark matter halos grow over thousands or millions of light years. Star formation happens inside dense clouds. Supernova explosions affect surrounding gas. Radiation moves through complex environments. Black holes, if present, add another layer. A simulation must handle gravity, gas dynamics, cooling, chemistry, radiation, feedback, and cosmic expansion. No simulation is the universe. Each one is a controlled approximation. When new observations arrive, the approximations are tested. Sometimes they pass. Sometimes they need tuning. Occasionally, they reveal that a missing process was important. Webb's role is to provide the kind of early universe data that simulations have never had at this quality. That is why the discoveries feel both threatening and useful. A model that is never challenged becomes comfortable. A model challenged by better data becomes sharper. The early galaxies are not embarrassing science. They are exactly what a powerful new telescope was built to find. The places where our previous picture was incomplete. The popular headline says the Big Bang is broken. The deeper headline says the first galaxies are more alive than expected. That is more accurate and, in some ways, more profound. A broken Big Bang would be a total collapse of the story. A more productive early universe changes the story from inside. It tells us that the cosmos reached complexity earlier, that the first structures were more capable, and that the road from simple matter to galaxies may have been shorter in some regions than almost anyone predicted. There is also a psychological reason these discoveries feel so powerful. The Big Bang has become a cultural symbol of the beginning. People imagine it as an explosion from nothing, a starting gun for everything that followed. When a telescope finds something strange near that beginning, it feels like the whole origin story is in danger. But the scientific Big Bang is not a cartoon explosion. It is a model of an expanding, cooling universe that was once hotter and denser. It does not say every detail of early galaxy formation was already solved. It does not require the first galaxies to be slow, simple, or dull. In fact, one of the reasons Webb exists is that astronomers knew the first galaxies were still mysterious. Galaxies themselves are not the surprise. What unsettles the models is how some of them look. That distinction keeps the video honest. James Webb has not proved that the universe never began in a hot, dense state. It has not erased the cosmic microwave background. It has not removed expansion, redshift, or the evidence from light elements. Anyone claiming that one distant galaxy alone has made the entire Big Bang theory worthless is going further than the evidence allows. Yet dismissing the discovery would be just as wrong. A galaxy at this distance, with this brightness and these signs of maturity, is a serious clue. It may reveal that some early galaxies grew in ways our models underestimated. It may show that star formation in the first dense halos was unusually efficient. It may strengthen the case that early black holes, bursty star formation, and rapid enrichment were common parts of cosmic dawn. The truth sits between hype and dismissal. That is usually where real science lives. One helpful comparison is the discovery that the universe's expansion is accelerating. Before the late 1990s, many astronomers expected gravity to slow cosmic expansion over time. When observations of distant supernovae suggested acceleration, the universe did not become meaningless. The old framework did not vanish overnight. Instead, cosmology gained a new, mysterious component: dark energy. The model changed because the data demanded it. Webb's early galaxies may not require anything as dramatic as dark energy, but they could still force a major adjustment. The change might be in how the first stars formed. It might be in how gas cooled. It might be in how black holes seeded and grew. It might be in how feedback worked in dense early halos. It might even point towards subtle changes in small-scale structure formation. The important point is that the answer remains open. A mystery is not automatically a revolution, but a persistent mystery becomes a direction. JADES GS Z140 gives that direction a name. It says, look earlier, test the brightness, measure the chemistry, find the population. Do not assume the young universe was slow simply because our old telescopes could not see it. From here, the story becomes almost detective-like. Astronomers will ask whether the galaxy's light is dominated by young stars or partly by an active black hole. They will refine the stellar mass, star formation rate, and dust content. They will search for more emission lines. They will compare it to other galaxies at redshifts above 10, 12, and 14. They will ask whether the surrounding region was unusually dense. They will examine whether simulations can produce similar galaxies without breaking established cosmology. Each answer will narrow the possibilities. If young stars dominate, then star formation was remarkably efficient. If black holes contribute, then black hole growth at cosmic dawn becomes more important. If chemistry is widespread, the first stellar generations must have begun very early. If the object is rare, it becomes a special case. If it is part of a large population, the entire early universe becomes more surprising. The next discovery may be even stranger. Webb is not looking at a wall. It is looking into a frontier. There may be fainter galaxies beyond JADES, GSZ140, that we have not yet confirmed. Some may be too dim for current spectroscopy. Others may sit in fields Webb has not observed deeply enough. A future record holder could appear at an even higher redshift, pushing closer to the time when the first stars turned on. At some point, though, observation must meet physics. The universe cannot form luminous galaxies before matter has had time to collapse. There must be a first star, a first cluster, a first galaxy, a first chemically enriched region. The record cannot move backward forever. Webb is helping locate where that transition actually happened. That is one reason the discoveries are so exciting. These observations are not just adding more distant objects to a list. Instead, they narrow the unknown interval between darkness and light. For decades, cosmic dawn was a wide blank space in the timeline. Scientists knew what came before, from the cosmic microwave background. They knew what came after from galaxies observed at later times. Between those eras was a gap filled by theory, simulations, and indirect evidence. Webb is now placing actual objects inside that gap. Each object turns the blank space into history. JADES, GS, Z14. 0 is one of the earliest clear marks on that map. The map is still incomplete, but it no longer feels empty. Another subtle point deserves attention. The phrase, universe was only 290 million years old, can accidentally make the early universe feel small, like a child version of the cosmos. In time, it was young. In scale, it was already vast. Space had expanded enormously since the hot initial state. Light from distant regions was already separated by horizons. Gravity was working in many places at once. Cosmic youth does not mean cosmic simplicity everywhere. Some regions were denser than others. Those regions collapsed first. If JADES, GS, Z14, 0 formed in a rare overdense area, it may represent one of the first places where matter won its race against expansion. A rare peak in the early density field could gather gas earlier than average, forming stars before more ordinary regions. This is an important way to reduce the tension. The first galaxies we detect are not necessarily typical. They are the brightest, luckiest, most observable examples. Webb is biased toward what shines. The easiest ancient galaxies to see are the ones that became luminous early, not the faint majority. Observing a bright galaxy at very high redshift may therefore tell us about the extreme tale of cosmic structure, not the average young universe. Extremes still matter. A mountain peak tells you something about the landscape, even if most ground is lower. If the peak is much higher than your model allows, the landscape model is wrong. If the peak is rare but allowed, the model survives. The task is to determine which case we are in. That requires statistics. Science cannot rest on awe alone. Astronomers need number counts. How many galaxies of a given brightness exist at each redshift? Luminosity functions then describe the distribution of galaxy brightness. Mass functions estimate how much stellar mass exists in galaxies at early times. Finally, those measurements must be compared against predictions. That is where Webb becomes more than a telescope of beautiful images. It becomes a measuring instrument for cosmic history. Every deep survey contributes to this measurement. JADES, KEARS, Cosmos Webb, UNUFA, and other programs all help build the population picture. Some fields go extremely deep over small areas. Others cover wider regions to find rarer bright objects. Together, they reveal whether the early universe was full of surprises or whether the most dramatic cases are rare exceptions. The answer will not arrive from one viral headline. It will emerge from many papers, many spectra, and many reanalyses. That slow process may seem less dramatic, but it is how knowledge becomes durable. In the meantime, the central mystery remains powerful enough for a long documentary. How could the universe become so interesting so soon? One possible answer begins with the dark matter scaffolding of the cosmos. Dark matter gathers first. creating gravitational wells where ordinary gas can fall. If the earliest halos were rarer, denser, or more efficient at feeding stars than expected, Webb would expose that immediately. The important move is disciplined. Test the astrophysics first, then ask whether deeper cosmology must change. Wonder does not require careless conclusions. JADES GS Z140 is real enough. The puzzle is real enough. The need for better answers is real enough. No exaggeration is required. Consider the role of oxygen again. In a young galaxy, oxygen is not simply a chemical detail. It is evidence of previous generations. Massive stars must have lived and enriched their surroundings. That means star formation began earlier than the moment we observe. How much earlier depends on the galaxy's history, the types of stars formed, and the interpretation of the emission. If a model requires star formation to begin at an extremely high redshift, then cosmic dawn shifts backward. The first luminous objects become older in the timeline. That does not mean they existed before the Big Bang. It means they appeared closer to the beginning than expected. The distinction may sound obvious, but in public discussions, it often gets lost. A galaxy too old for our simple model is not a galaxy older than the universe. It is a sign that our simple model of its formation may be incomplete. This is exactly the kind of correction Webb was built to provide. Before Webb, astronomers had to infer too much about the earliest galaxies. Now, light from those galaxies is being separated into spectra. Photometric guesses are being replaced by redshift confirmations. Mid-infrared detections reveal rest frame optical features. Sub-millimeter observatories test gas and chemical content. The first chapter is becoming empirical. That word, empirical, is the quiet revolution. The early universe is no longer only a theoretical wilderness. It is becoming observable territory. When a territory becomes observable, old maps fail in specific places. Rivers are moved. Mountains appear. Distances are corrected. The map is not burned. It is redrawn. Webb is doing that to cosmic dawn. Maybe the first galaxies were more compact than expected. Maybe their stars formed in shorter bursts. Maybe early feedback cleared dust and gas in ways that made them suddenly visible. Perhaps black hole growth and galaxy growth were entangled from the beginning. Maybe the most luminous galaxies at extreme redshift are rare phases rather than stable, mature systems. Each possibility gives a different shape to the first light. The most exciting outcome may be a mixture. Nature rarely chooses one clean explanation. JADES GS Z140 may be bright because of efficient star formations, unusual stellar populations, rapid enrichment, and favorable conditions in a rare early halo. Other early galaxies may involve black holes or dust. The population may be diverse from the start. That would change the mood of cosmic dawn. Instead of a simple error of tiny primitive galaxies slowly growing, it becomes a chaotic landscape of bursts, collapses, mergers, radiation, and chemical change. Some regions remain dark. Others ignite early. A few become extreme enough to reach us through Webb's instruments more than 13 billion years later. This picture feels less orderly. It may also be closer to reality. The universe is not obligated to be pedagogical. It does not arrange its history in neat chapters for our convenience. The first stars, galaxies, and black holes may overlap because gravity works wherever conditions allow. In the densest early regions, several processes can begin before the average universe catches up. The next major step is precision. Astronomers need better spectra for more early galaxies. Measurements of oxygen, hydrogen, and other emission lines will reveal the chemistry. Dust, temperatures, gas reservoirs, and star formation rates must be constrained. Starlight has to be separated from black hole light. Sizes, shapes, and possible lensing magnification all have to be checked before the physical story becomes secure. Each measurement reduces ambiguity. For JADES, GS, Z140, the record redshift is only the beginning. The most important future work concerns the physical interpretation. How massive is it really? How intense is its star formation? How enriched is its gas? How old are its stars? What does its size tell us about the halo that formed it? Could an active nucleus be present, or is stellar light enough? These questions may sound technical, but they all aim at the same deeper issue. How fast did the universe become complex? Answer that, and the title of the video becomes clearer. The James Webb discovery could change the universe not by changing what happened, but by changing the universe we carry in our minds. For decades, the first few 100 million years were often imagined as a slow fade-in. Webb suggests the fade-in may have contained flashes, bursts, and early engines of growth. The first light may not have been gentle. It may have been intense. At this point, the viewer may wonder whether there is any limit to how early galaxies can appear. Could Webb one day find a galaxy only 100 million years after the Big Bang? Could it find something even earlier? The answer depends on what we mean by galaxy. A first star is not a galaxy. A small cluster of stars inside a dark matter halo may be a proto-galaxy. A system bright enough to be detected across cosmic time is another threshold. The word galaxy becomes less clean near the beginning, where the first structures are still assembling. This is another reason the frontier is difficult. At later times, galaxies have recognizable shapes: disks, spheroids, irregulars, mergers. Near cosmic dawn, the categories blur. A luminous clump may be the beginning of a galaxy, rather than a mature galaxy. Several clumps may later merge. Gas may dominate over stars. The structure may be temporary, bursty, and violently changing. Calling it a galaxy is useful, but it can make it sound more settled than it was. JADES, GS, Z140 is not a spiral like the Milky Way. It is not an ancient version of a modern galaxy, calmly rotating in space. It is a young system seen at an extreme time, with properties that force us to ask how early organized starlight can become visible. That nuance keeps the wonder sharp. The discovery is not amazing because it is basically the Milky Way appearing too early. It is amazing because it is a real, luminous, chemically interesting galaxy when the universe should have had very little time to make one. There is another hidden consequence. If galaxies formed and enriched their surroundings earlier, then the raw materials for later generations also appeared earlier. Heavy elements are necessary for rocky planets, complex chemistry, and eventually life. Nobody is suggesting life existed near JADES, GS, Z140 at 219 million years. The environment would have been harsh, young, and chemically primitive compared to later cosmic history. But the first steps toward the ingredients of planets had begun. Every oxygen atom detected in such a galaxy is part of a chain that eventually leads to worlds like ours. Not directly from that galaxy to Earth, but through the cosmic process of stellar alchemy. The universe had already begun making the materials that future complexity would require. That gives the discovery a quiet, emotional dimension. This is not just old light. Through it, we see the early universe start to make the periodic table richer. The atoms in our bodies come from stars. Webb is watching an era when that long chemical story was beginning. In a deep field, a faint galaxy becomes a clue to the origin of oxygen, dust, and the first enriched environments. The connection stretches across almost all of time. A viewer lying in bed at night may hear that and realize something simple but profound. The universe did not wait long to begin the chain that made observers possible. The first steps happened early, maybe earlier than our models comfortably expected. This is where the narrative can return to the Big Bang question. A weak version of the story says, Webb found an old galaxy, so the Big Bang is wrong. A stronger version says, Webb found a galaxy so early and so developed that we must rethink how the first cosmic structures formed after the Big Bang. The second version is less sensational, but it is more powerful because it can survive scrutiny. It does not collapse when a scientist explains the cosmic microwave background. It does not depend on pretending one observation has overturned a century of evidence. It invites the viewer into the real mystery, where the foundations remain strong, but the upper floors are being rebuilt. For a documentary channel, that is the better story. It builds trust. It creates tension without lying. It leaves room for future episodes as the evidence changes. And the evidence will change. Webb is still young as a mission. Its deepest surveys are continuing. Instruments are being used in new ways. Astronomers are learning how to interpret the strange objects it finds. ALMA, Hubble archival data, ground-based observatories, future Roman surveys, Euclid's wide cosmic maps, and perhaps future extremely large telescopes will all add context. The picture 5 years from now may be sharper than the picture today. Some mysteries may fade, others may grow. That is normal. The first wave of Webb discoveries created excitement and confusion. The second wave began sorting candidates from confirmed galaxies. The next wave will build populations, measure chemistry, and refine models. Over time, the question will change from what did Webb find to what pattern did Webb reveal. Patterns are where cosmology becomes dangerous for old assumptions. One galaxy can be rare. 10 can be surprising. Hundreds can change the field. If Webb and future observatories find that early bright galaxies are common, then the universe's first few 100 million years must be rewritten in detail. Textbooks may still include the Big Bang, expansion, and the cosmic microwave background. But the chapters on first stars, early galaxies, black holes, dust, and reionization would look different. That is what change the universe means in the responsible sense. It means change the universe as understood. The timeline changes. The expected pace shifts. The first chapter turns from a slow emergence into a faster, stranger ignition. Near the end of this story, it is worth stepping back from the measurements and imagining the scene itself. No human eye could have watched JADES GS-Z140 when its light began traveling. There were no eyes. There were no planets with oceans under blue skies. There was no Milky Way as we know it. The sun would not form for more than 9 billion years. Earth was not even a future dust cloud yet. Across a young cosmos in one dense region, matter gathered. Gas fell inward. Stars ignited. Some stars burned with extreme power and died quickly. Their ashes enriched the gas around them. More stars formed. Light escaped. Then, that light began a journey through expanding space. For more than 13 billion years, it traveled while galaxies merged. Stars were born and died. Planets formed. Earth cooled. Life emerged. Animals evolved. Humans looked up. Civilizations rose. Telescopes were built. And finally, a golden mirror unfolded far from Earth. Webb caught the light, a signal from a time before almost everything familiar. That is the emotional core of the discovery. The problem it creates for theory is important. The numbers matter. The redshift matters. The oxygen matters. The models matter. But beneath all of that is the astonishing fact that humans can now ask detailed questions about a galaxy that existed when the universe was only a few % of its present age. That ability is new. For most of history, the beginning was myth, philosophy, or mathematics. Now the beginning has data points. Tiny, faint, difficult data points, but real ones. And they do not simply confirm what we expected, they speak back. The young universe was not easy. The first galaxies may have grown quickly. Early stars may have transformed their surroundings sooner than expected. Black holes, dust, gas, and radiation may have joined the story earlier than our simple models allowed. The Big Bang may still be the beginning, but the aftermath was wilder than expected. That is a better ending than destruction. A destroyed theory leaves only rubble. A challenged theory leaves a path forward. James Webb has given cosmology that path. It has not handed us a final answer. It has opened a deeper question and placed it in the sky as a faint red galaxy. What happened in the first 300 million years? How many galaxies were already shining? How much chemistry had already begun? Were black holes growing in the dark? Did the first stars form in ways we have not fully understood? And was the universe, from the very beginning, far more efficient at creating complexity than we imagined? These questions do not make the cosmos smaller. They make it larger in meaning. The observable universe contains billions of galaxies today, but Webb reminds us that the story of those galaxies began in darkness, with fragile first structures forming from tiny fluctuations. Somewhere in that darkness, the first stars lit. Somewhere the first heavy elements appeared. Somewhere the first galaxy bright enough to reshape its surroundings began to burn. JADES GS Z140 may not be the first galaxy. It is almost certainly not the absolute beginning of starlight. But it is one of the earliest confirmed glimpses we have of that transition. It stands close enough to the beginning to make our models uncomfortable, and clear enough in the data that it cannot be dismissed as a simple mistake. That is why it matters. Not because it ends cosmology, because it gives cosmology a sharper frontier. The universe did not become understandable when Webb launched. In some ways, it became more mysterious. The telescope removed one darkness and revealed another. Not the darkness of empty space, but the darkness of incomplete knowledge. That is the most valuable kind. It can be explored. As more light reaches our instruments, the old timeline may keep changing. The first galaxies may move earlier. The first black holes may appear more quickly. The first chemical enrichment may become less rare. The first billion years may turn from a quiet dawn into a crowded, violent, creative era. If that happens, the Big Bang will not be remembered as a theory Webb simply broke. It will be remembered as the foundation beneath a story that became richer when we finally saw the first galaxies clearly. The discovery could change the universe, because it changes the beginning of the universe's visible story. It asks us to replace a slow, empty dawn with something more intense. In that cosmos, the first lights came on sooner. Matter organized itself faster. Complexity did not wait politely for billions of years before making its first move. And perhaps that is the most haunting part. When we look into the deepest Webb images, we are not only looking at what the universe used to be, we are looking at what the universe was already capable of becoming. The faint red galaxy is not loud. It does not look like a revolution. It is small enough to hide in a field of distant light, easy to miss unless you know where to look. Yet inside that tiny signal is a challenge to the story we tell about cosmic dawn. The opening chapter may have been faster. Those first fires may have been brighter. Chemistry may have begun sooner. Early structures may have been more powerful than we expected. James Webb did not travel back in time. It waited for time to arrive, and when that ancient light finally reached its mirror, it carried a message from near the beginning. The universe was young. The darkness was deep, but already something was building. And that may be the discovery that changes everything.